All right. It looks like our class is getting smaller as the weeks go by. Anyway, a couple of quick things. I sent an email already. I've added a couple of simulations, a couple of extra ones to help you out with respect to a couple of things, shapes, and there you go, Jackie. The important ones. That's a good one. Yep. Um, Shapes and polarity. But let me go to that website just to make sure that you know where they're at. I put them under the modules. Um, Jordan. um, I put them under the modules and scroll down to additional resources, and you'll find the last two one labeled molecule polarity and molecule shapes. Okay, so all right, guys, let's not get too crazy with the chat now. So what happens with when you click them? Well, when you click them, you get, let's go to the shapes one. You get simulations. These are simulations run by the University of Colorado. They have a multiple different ones. And anyway, it's just a topic. So if you have children out there, these are good simulations for, they range from grade school all the way up to college simulations. So might check into it. Let's take a look at the shapes. You can take, let's say, a particular atom. No, we don't have to be concerned about what it is. We got one. And then if you look in the top right corner, you see single, double, and triple bond. So let's add a single bond. And that's three-dimensional, so you can grab it and move it around. You can see just two atoms are simply linear with respect to geometry down here in the bottom left-hand corner. Okay. Now let's add a second one, the second bond. And notice what happens is if I try to bring that other bond close to the first bond, it won't work. And why is that? Well, think about this for a second. All of this, all surrounding all this is, hold on, I got a couple people here. Let's get them all in. Okay. And so electrons, the gray area, that bond, that all this, whatever marking here, you can see that's electron density. And being electron density, they're going to want to pull away from each other. So what they want to do is as I put one in, they just want to get far apart from each other. So in this configuration with three atoms, we got a linear configuration. Now let's add a second one, a third bond. Notice what happened. Again, because the electron density in the bonds, they want to repel from each other. And so they want to get the maximum separation from each other. And so when I have three things bonded to the central atom, I end up with this particular configuration, which is trigonoplanar. Now we add one more bond. And again, now we have what's called the tetrahedral. And even trying to bend the bond closer together, it won't work because the electrons are repelling from each other. And so this is the configuration that maximizes that repulsion of the electrons, and then we end up with the tetrahedral. Now, if we take out one of those bonds, we're back to the planar uh, configuration, but let's add a lone pair. Sticking a lone pair into the central atom, look what happened to that angle. Those lone pairs, again, two of them being in that orbital, take up a lot of space. So they shove the bond even further away from each other. And we end up with this configuration, the trigonopyramidal. Let's take out one of the single bonds and add another lone pair. Now we have the Bet configuration with two lone pairs in the central atom. So those lone pairs have a lot to do with respect to the effect the um, the uh, um, the configuration of the molecule, what the effect of what type of configuration it has. Now, let's shoot over to the polarity simulation. Okay, so here we have two atoms represented by A and B. Now, down at the bottom, you'll see the electronegativity. Right now, I got them set for less. They're both set as equal. And we have basically similar electron density around both A and B. We end up having a nonpolar bond. Now, and that's the case for any of the diatomic molecules that we have no fear of ice cold beverage, and any carbon hydrogen, because the electronegativity of A and B is either they're very close or the same, and therefore we have no dipole. Now, the moment I change the electronegativity of one of the atoms, and we're going to just arbitrarily take B and start increasing the electronegativity, first thing you notice is the B side gets a little darker in color. That represents that the electronegativity of B is getting greater, and then that is a measure of the pull of electrons toward itself in the bond. Also generated at the time, I'm showing electron density, but we also can show it by using what's called electrostatic potential, where the negative color represents a high negative charge and the blue represents a low negative charge. Okay. Now, got a couple more people in. Let's let them in. All right. I tend to like the electron density color better because it does show the darker color versus the lighter grayscale color, with the darker color showing more electron density around it, compared to the A, which now has a little bit lighter shade of gray. We've also generated the dipole arrow. There was some confusion about the arrow. The arrow, the point of the arrow points toward the most electronegative element. Here in this case is B. And the little plus sign on the tail of the arrow points is in the direction of A, that atom that has the least electronegativity. Okay. So we created a dipole. So we have a dipole, a polar bond here. And it really isn't that complicated. If you think about this, it's very straightforward. Whenever you have two different atoms, plain and simple, you got a polar bond, with the exception of carbon hydrogen. That's it. You don't really need to think about it. I've been grading a lot of the Lewis dot structures, and I've been seeing things like, well, carbon, oxygen, and fluoride, that's not a polar bond. Yes, it is. Two different atoms. It's extremely polar, especially with fluoride being bonded. Okay? And so, straightforward. Two different atoms, polar bond, except for carbon hydrogen. Now, what effect does that have? And I have a video that I'm going to show you. I can't find it, but I will show you how you can charged particles are affected by electricity. And you can do this at home. If you go to the sink and you get start the water up for a very fine flow of water, okay? And get yourself a comb and comb your hair, okay? Pull those electrons off your hair. Take that comb and very carefully, in that stream of water that's running in your sink, come up against it. You're going to see that stream pushed away or pulled toward the comb. Okay. Okay. With respect to multiple, Brian has a question. Question is, what about multiple atoms? The same scenario, and I'll demonstrate that. When you do multiple atoms, you look at each individual bond and you ask yourself the same question. Do I have two different atoms? If they are different, you got a polar bond, okay? Case in point, we did the example of carbon dioxide. When we did the Lewis dot structure, we found it to be nonpolar, but I'll come back to that here in a second. The fact that we created a dipole bond, it has, and if we put an electrical field around it, it's affected by the electrical field. Here's a couple plates with a positive and negative side. Those particles are affected, and the negative or the partial negative will be attracted to the plus plate of this electropotential. That is actually what's happening if you ever had an MRI done and you are put into that tube. You're put into a gigantic magnet as you go through that tube. And what's happening there is lining up all the hydrogen atoms, because the electron rotating around the hydrogen atom has a magnetic component. It has a pole. And as you go through that magnet in that MRI, all of your hydrogen atoms are lit up and all straighten up in a certain direction. Okay. Anyway, the question was multiple shapes. Well, to demonstrate that, let's go back to the shapes simulation. And let me go back to real molecules here. Let's see if we got a double. Oh, yeah, carbon dioxide. Okay. We got carbon dioxide here. Here's the structure. Now, we went through the example here when we were doing the Lewis dot structure, but this is carbon in the central atom and oxygen denoted by red. Two different atoms, we have a dipole. Okay. You go to the other side, carbon and oxygen, totally different oxygen, two different atoms. Guess what? We have a dipole. So those two bonds are polar. But the fact that they are going in opposite directions, they cancel each other out with respect to the effect of the polarity of that bond. Okay. That being the case, carbon dioxide ends up to be nonpolar because the polar bonds in multiple atoms here, in the multiple bonds, cancel each other out. Now, if I were to get, let's see, this one, this is sulfur dioxide, where, let me clear this up. Again, the question was, Nathaniel had a question, if one of the oxygens was a different element, makes no difference because you look at each bond individually, okay? And you determine whether it's a polar bond. And now I would do that here also. I'll give you another example. So let's go back to this one here very quickly. And we have sulfur dioxide. Here, again, we have a polar bond between the sulfur and the oxygen. And so between the sulfur and the oxygen, we have a dipole, okay, going from sulfur. Sulfur is the mustard colored and the red color is the oxygen. And then in the other side, we have another dipole. But unlike the case with respect to carbon dioxide, where the dipoles are going in different directions and they canceled out, that's not the factor here. Because of those lone pairs sitting right there, that bond angle is no longer at 180 like carbon dioxide would be. It is actually at much less than 120 here, actually about 120, less than 120. And the dipoles are going in different directions, so this molecule is polar. It has polar bonds, two polar bonds, and because the polarity is different and going in different directions, it ends up in polar. You end up with a polar molecule. Let's say let me see, they got one here. Yeah, this one right here. Yeah, that's a bad example. You need, okay, we'll go with this one. Okay, this is methane. Okay, but let's assume for a moment that all four of these moieties bonded to them were something else. Maybe they're all different halogens, fluoride, chloride. Okay, if they were all chlorides, they all have a four polar bonds. Everybody agree on that, right? But because of the geometry of the tetrahedral, all those four polar bonds, if everybody was a chloride, all the four bonded items were chloride, they will cancel out, and then this compound would be nonpolar. Now, if I replace one of them with something else, regardless of what it is, and now I have three chlorides versus something else, maybe a hydrogen or a different halogen. The fact that three of them are polar with a different magnitude between the fourth one, we end up with a polar bond. Okay, so what do I mean by that? Well, let's say this one was Cl. And this one was also Cl. I'm going to try to line them up so they can. And this one here was Cl, chloride. Okay. And so here, and we'll keep the last one as hydrogen. We got three polar bonds. Okay. The bond between carbon and chloride, we got a dipole. But they don't cancel out. The three don't cancel out. Okay. We have a net polar molecule here. And even if I were to replace the last one with, let's say, Br, okay? And so I got three chloride bonds and one bromide bond. All of them are polar bonds. They wouldn't cancel out because in each case, there's a different magnitude of polarity. The three chloride bonds would have the same magnitude, but the bromide would be a different magnitude because it has a different electronegativity. The result would be that this compound would be polar, okay, because it would be still a slightly more polar magnitude overall. Okay. And
I have a question.
sure, go ahead.
What if it was like the opposite, to where there was three non-polars and then one polar? Would it still be polar because that one? Okay.
You got it, exactly. If this was all back, let's cancel. The question is, what if it was all um, one and we just change one and maybe make this one any halogen? I'm just going to call it X. So that's being either bromine, chlorine, or iodine. The fact that we got one polar bond going in that direction. Okay. So then I'm getting, I got somebody in. One moment. Okay. Okay. The fact that we got one polar bond, there's no polar bond between the carbon and the hydrogen. Okay. And so we got three zeros, but yet we got one bond that still has a net polarity. And even if I change the other two, this go all the way around the horn and make this another one with an X, I still have a polar bond, two polar bonds, two non-polar bonds. My net is polar molecule. And then I continue and do X again for the third one. Again, because I have one polar, non-polar bond, my net is still, I got three polar bonds, so my net is still polar. Not until I go around the horn and I make the last one with X, and they're all the same. That's important. They're all the same, either all chlorides, all bromides, or all iodides, or whatever you want to put up there. Then I'm back to a nonpolar molecule because in that configuration, they all cancel out. The polarity cancels out. Okay? All right, so these simulations will help you out. You can play with them. There's all kinds of different examples you can do, and they give you a better understanding about. Let me clear this out here. Uh, Actual three other molecules that you can work with, and you can see their configuration and so forth. Okay. All right. Let's go back to, so where we ended up was in slide here, where we were looking at taking a sentence and from that sentence decipher it and write that sentence into a chemical reaction. Okay. And it's very important that we read it properly, because we're not going to be with it, because remember, all the nonmetals change their name once they become ionic. All right. So here we have aluminum reacts with bromine to produce solid aluminum bromide. And so here we got aluminum all by itself, and there's nothing else following it. So that's automatically, that is the elemental aluminum, good old Al or Al. Reacts with bromine, not to be confused with bromide. So the INE tells you I'm dealing with the element bromine. And then take it one step further, bromine is one of the 7 diatomic molecules, so I have to know its formula. So it's Br2, because we know that bromine, chlorine, iodine, hydrogen, oxygen are all diatomic. Have no fear of ice cold beverage. And then they tell you the keyword to produce. To produce is the keyword to tell you that's the arrow, the reaction arrow. To produce, so anything after to produce or forms, the word forms or reacts with, anything after that are the products. And so they tell you solid, there's the physical state of it, aluminum bromide. Well, it's important that we first write the proper formula. So we break down aluminum bromide into the ions. And that's where your knowledge of what type of ion with respect to charge they are. Okay, because without that information, you're not going to be able to put them together in the correct ratio to write the formula. And so if you forget, go to the periodic table, search out aluminum. Aluminum 1 is a metal. And remember, long-term memory, all metals lose electrons. So whatever number of valence electrons that metal has, it's going to lose them. We find aluminum to be in group 3. There's 3 valence electrons, so therefore it's going to lose those 3 electrons because it's a metal, giving me a +3 charge. Okay. Then we look at bromide. The key suffix is the IDE, which tells you that you're dealing with ionic bromine. And so we go to the periodic table, find where bromine is. It's in group 7. It becomes an ion by gaining 1 electron to give us the octet. And so bromine has now an extra electron, or excuse me, bromide. So it has a -1 charge. So this is what I mean about when you're given the name, breaking down to the ions first. When you're given an ionic compound, break it down to the ions, then figure out how many of each I need. Because we know that to put them together, they have to net 0. I have to put enough cations to counter the number of anions to give me a 0 charge. Since aluminum has a +3, I must need 3 bromides to cancel the +3 coming from aluminum. So that 3 now becomes the subscript for AlBr3. Now, this may sound like overkill, but I think, It's a good rule of thumb. If one of your instructors is repeating something, it might be important. It might be coming up. Okay, so and I'm also trying to show you how to look at this and break it down stepwise. Sometimes one reads the question and it get overwhelmed because there's so much information there. And the best way to attack something like that is to break it down into steps of what you know and then put it all together. So that being the case, now we can write a proper reaction formula, okay, with the correct formulas. Again, we have aluminum plus a Br2 reacts or to produce, which is the arrow, aluminum bromide, okay? Now we got to put the states, okay? And so refresh your memory about the states. There's a limited number of gases, there's a limited number of liquids, and everything else is a solid. Okay. Do you anybody remember who of the 118 elements we have, how many were liquids?
Was it 2?
2.
You got it. Okay. You remember who those two were?
Mercury and
Bromine?
Bromine, exactly. So we know that aluminum is not a gas unless it's on the surface of the sun. But here on Earth, aluminum is a solid. Okay. Because the physical properties, remember, those are 25 degrees. Physical properties like boiling point, or whether it's a liquid, gas, or solid, is dependent on the environment. And at 25 degrees, aluminum is a solid. Unless it's in a furnace, and then we're talking liquid here. Bromine is a liquid, and you're given from the word problem, from the sentence, that it's solid aluminum bromide. So now you got all the physical states of your reactant and products. Now the next step is to balance the reaction. Now, some of the reactions, it's a matter of trial and error, unfortunately. When we get into chemical reactions, the other ones, we have little tidbits to help you with balancing, but some of them we got to kind of play with the numbers a little bit, but not all, because if you look at this reaction, you take a look at this, just like we were putting atoms, ions together. Normally it was a 2-to-1, 3-to-1. Aluminum bromide was, here it is, the 3-to-1. But remember when we came up with the one with a +2 charge and one was a -3 charge? One of the things I said was, hey, find a common number, just like you're trying to add 1/4 plus 1/5. Find a common denominator. And in that case, it was 6. Well, you can continue with that because you can see here that I got 3 bromides over here and 2 as reactant side. Okay. So I got a 2-to-3 ratio going on here. I can tap into that. That differences, and I can say, okay, my common factor must be 6 for the bromines. And sure enough, if I put a 2 in front of aluminum bromide and a 3 in front of bromide, I have my bromines balanced. So I put a 2 there, I got 3 bromides and 3 on the left side. Now, by putting the 2 in front of aluminum bromide, I've upped my number for aluminum, so I got to balance aluminum now, and it's a simple matter of putting a 2 in front of aluminum. And so now my ratio is 2 aluminum per 3 bromides, okay? So let me ask you a question. If I have 10 aluminums, how many bromines do I need? Okay. What if, right, my balanced chemical equation says that I need two atoms of aluminum for every 3 bromines. But what if I had 10? How many bromines would I need?
Are we doing bromine or bromide?
No, bromine. Right now, see that question mark I put under in blue?
I would say 10.
10? Okay, no, I have 10 aluminum. How many bromines, Br2, do I need? What number should I replace that question mark with?
Okay, I think I might know it, but it's probably gonna sound really wrong. Would it be 30?
Not quite.
Okay.
Okay, it's okay.
I'm trying to do the math in my head.
Yeah, it's all right. It's all right. And so look at it this way. How many more aluminum do I have now from the balance chemical equation? What factor did I increase? I went from 2 to 10. What's a factor of what? What's 2 divided by 2? 10 divided by 2?
5.
5. And so how much would I have to increase bromine to keep that same ratio?
15.
You got it. Okay. Because that ratio, 2 aluminum to 3 bromine, that's a constant. That's a balanced chemical equation. And so if I want to run that reaction, but instead of starting with 2 aluminums, I start with 10, I need at least 15 bromines. Okay. Another way of saying this, and I bet you guys will get this, right? All right. All right. We all agree, well, hopefully we agree, that I'm going to take the example of a bicycle. We all agreed that I need one frame. For one frame, I need 2 tires. Everybody agree on that, right? Kind of hard to ride that bicycle with 1 tire, unless you want to make it into a unicycle. Now, what if I had 30 frames? How many tires would I need to assemble those 30 frames?
60.
Exactly. Okay. I would need 60. Okay. Now, if I had I don't know, let's say 10 tires, how many bicycles could I assemble? How many frames do I need?
5.
Okay. You need 5. Okay. And you just did in your head, those of you who worked that using the bicycle, you just did stoichiometry. Now, for some reason, I don't know why, and I'm still trying to figure out why. Now, instead of frames, I say aluminum, and instead of tires, I say bromine. It gets complex. Okay. But the same thought process of you figuring out the frame and tires, okay, we use here because we have a ratio. I mean, I could have gone, okay, this is a 2-wheel bike. What if it was a tricycle? Okay. So if I have, I need to know how many frames I have, and I got 30 tires for a tricycle frame. Okay, 5 frames, and I have 30 tires. How many tricycles can I have assembled?
10.
Exactly. Okay. Exactly. And working backwards, if I need 50 tricycles assembled, don't I need 50 frames and 150 tires? Right? And that's the kind of stuff that we'll be doing, but instead of tires and frames, we'll be doing chemical reactions. So to work that one, if I had 10 aluminum bromides, if I had 10 aluminum bromides, okay, how many aluminums would I need? If I need to make 10 aluminum bromides, how many aluminums would I need to start off with?
5.
Sure. Okay, look at the ratio, the coefficient in front of aluminum. Look at the coefficient in front of aluminum bromide. What does it tell you? 2 to 2, right? Or it's a 1 to 1, isn't it? So if I need 10 aluminum bromides, I'm going to need 10 aluminums to begin with. Does that make sense? Clear as mud, right? Okay. Well, that's okay. Because this is the beginning of what we're going to be doing when we have balanced chemical equations and we start calculating it. Okay? Because we have to balance a chemical equation. Why is that? Because those coefficients on front, guess what they do? They set up a ratio. Remember the ratios we did when we were doing the conversion factors? 1 inch is equal to 2.54 centimeters. And I said at that time, you can write it with 1 inch in the numerator and 2.54 centimeters in the denominator, or vice versa, right? And which one you need depends on the units. And I kept overemphasizing the units, follow the units, because here, once we balance a chemical reaction, we have a ratio. That ratio, for example, is 2 aluminum to 3 bromines. So I can write it like there, the first one I've written there, or I can invert it, okay? 3 bromides in the top to 2 in aluminums. And which one I need depends on the question that I'm researching for. Those examples I did with the bicycle and the frames, those are also ratios. I could have set that up, that 1 bicycle frame in the numerator for a 2-wheeler and 2 tires in the bottom, or two tires in the numerator and 1 frame in the bottom. And then depending on the question being asked, I know which one I got to multiply, which factor I use in my multiplication, okay? Now, I'm just using the reactants, but I also have the ratio of, if you look at the ratio of aluminum to aluminum bromide, it's a 2 to 2. The ratio from here to here is 2 to 2. Isn't that 1 to 1? If I put that in a ratio, 2 aluminum over 2 aluminum bromide, don't the 2's cancel out? That's a 1 to 1. You all see that? And so if I needed 10 aluminum bromides, if I started with 10 aluminum bromides, I need 10 aluminums. Okay. But more on that down the road. So this is just the beginning of first balancing the equation and then recognizing the ratio of reactants or the ratio of reactants and products.
Question.
Sure, go ahead.
So how you got 3 Br2 in because you're balancing it out. Why is the 3 not in the aluminum bromide?
Okay, the 3 is the aluminum bromide already has 3 bromides.
Mm-hmm.
See, so there's 3 molecules of aluminum bromide, and so let me restate that. There's 3 atoms of the bromide tap into the aluminum, and I got 2 of those, and so 2 times 3 is 6.
Okay.
And with bromine, there's 2 bromine atoms for each molecule. 3 times 2 is 6.
Okay, I see what I was doing wrong. I was thinking like the 2 is like there's 2 aluminum and 1 bromide rather than it's aluminum bromide. That's what I was. Okay.
There's exactly three on there. Let me see if I can. draw this. Maybe. I have the, no, wrong one. There's aluminum, and there's 3 bromides bonded. Okay, you see how that works? Terrible drawing there, but I'm trying to play with a new toy, and it's not cooperating. So
Yes, I see what you're saying. I was just looking at the aluminum bromine as aluminum and then bromine
right.
rather than just the one thing. So I was like trying to figure it out, and then after I figured that out, then everything else became clear.
Okay, sounds good then. So yeah, and if I have two of these guys, my table. If I have 2 of these, so much for that. Well, never mind. You get the gist of it. I don't know why my little. If I got 2 of those molecules, then I got total 6. All right. All right. Let me go back to that. All right. So we balance these reactions. From the balancing of the reactions, we come up with a ratio. There's a whole chapter called stoichiometry. That's what we're doing here. We're looking at the ratio of the reactants and products. And from that information, we're going to be able to do calculations of going from products to reactants or reactants to products. So here's another question, another one. Written out, they're asking you to write the reaction. They're saying the reaction of phosphorus. Write the reaction of phosphorus reacting with oxygen to make solid diphosphorus pentoxide. Okay, and so we have phosphorus, nothing else, just the word phosphorus. So that's elemental phosphorus, so that would be P. Reacting with oxygen, so the term reacting means plus oxygen. And what do we know about oxygen? It's diatomic. And then to make means, that's the code word for the arrow. And then they're telling you solid diphosphorus pentoxide. Well, before I even do anything, I look at the product and I need to write the formula. Okay. And so now I got prefixes. So that tells you I look like I got a covalent compound. Now, I would recommend, like we did with the ionic compounds, writing the ions first and then putting them together. With respect to covalent compounds, look for the parent name first, which would be phosphorus oxide. Okay, so phosphorus oxide is simply P and O. Okay, that is the parent name. Now I go back and I double check my prefixes, and prefixes for phosphorus is di, so that tells me I need 2 of those. Okay, and penta, what does the pent prefix mean? 5, exactly. And so now I know what my formula is. So it would be P2O5. So now I can write the reactants. Phosphorus plus oxygen, which we know is a gas, and phosphorus is a solid. And they're told what the product is. It says it's a solid. Okay, so now we wrote the formula, but we're now balanced. Okay, now take the Q like we did in the last equation. We have an indifference here with respect to see when I see an element all by itself, I leave that guy alone. Work on the other species, because that element by itself, I can utilize at the last to add numbers in front of it to balance out. But the oxygens here, there's a disparity. I got 5 as a product and 2 as a reactant. No problem. Like we did the 2 to 3 here, our common number is 10, excuse me. So if I put a 5 in front of the oxygen, and if I put a 2 in front of diphosphorus pentoxide, that balances out my oxygens. But then that kicks up my phosphorus to 4. So now I got to balance the phosphorus out by adding a 4 in front of it. And now I have a balanced chemical reaction. Okay? Now, what if, let me ask you a question here. What if I had 8 phosphorus? Oh, come on. 8 phosphorus. How many oxygens would I need?
Would be 20.
20?
10.
10? Okay. Look at that ratio between, let me set it up. 10 is the correct answer. Okay? But let me do it this way. If I start off with 8P, okay, I need a conversion factor. That's my ratio. And the question is oxygen. Well, how many oxygens do I need? I don't know that. So that's going to be the numerator. Remember the conversion factors we did? So what is my ratio between oxygen and phosphorus? Isn't that 5? I'm just going to do O over 4P. Isn't that my ratio from the balanced chemical equation?
Yes.
Yes. Okay. Now, mathematically, do not my P's cancel? And what is left? Oxygen. I didn't put the O2, but, you know, that's oxygen. And so now my units cancel like they do properly, leaving me with units of oxygen, which is what the question was asked. And so 8 times 5 divided by 4, what do I got?
You got 10.
Exactly. 10, not O, but O2s, okay? 10 O2s, okay? And if I would have said 10,000 P's instead of 8, but then I would use that same ratio, 5 to 4. Because this ratio, 4 to 5 ratio, whether I do it in the lab in gram scale or whether I do it in the industrial scale in a big giant lab, that ratio is still the same. Still the same. Okay. Now let me ask you this, since we're on what if I need to make 100 PT05? Okay. Question is, how much phosphorus do I need to start off with? Okay. And so you're the chemist. Boss comes to you and says, okay, Mr. Chemist, I'll need you to make me 100, and right now we're just going to say molecules. 100 molecules of diphosphorus pentoxide. How much phosphorus do you need to start off with? Well, what do? No different than we did right now. Go ahead. Anybody want to take a, as they say, take a gander at that number?
Would it be 200?
200. Okay, well, let's work it out. Let's find out. All right, so what am I given? I'm given 100. And remember, I don't have subscript. P2O5, correct? That's what I'm given. Now, I need to know how much phosphorus I need, but what is my ratio of P2O5 to phosphorus? From the balanced chemical equation, isn't that P? divided by 4p. Isn't that my ratio?
Wouldn't it be the other way around? So that you can cancel out the PTO5?
Good, you got it. Very good. Because I'm looking for phosphorus, right? So I need to go phosphorus on top. Okay. And I need to go with 2p. Let me put a space there so we know. Okay. Which is good because what you do is you check your units once you set it up. Now, the way I had it before, my next step would have been check my units. I would have been multiplying P205 times P205. So that tells me, hey, I set something up wrong. But here, can you see where P205 cancel out in the math?
Mm-hmm.
Yep. And now it's a matter of doing the numbers. So it's 400 divided by 2, which gives me
200
200. 200 what?
phosphorus.
Phosphorus. Exactly. Okay. And you can see that my P2O5s cancel out, leaving me units of phosphorus, just like we did back when we're doing conversion factors. Okay. From units to units. The only difference now is we have new conversion factors that happen to be the ratios from the balanced chemical equation. So it's quite crucial that you balance it correctly. Otherwise, your numbers will be incorrect. If it was balanced 4-to-1, then we would think that you would need 400p, but it's not because the ratio is a 4-to-2 ratio. Okay. Now, I could have asked the question, well, how much oxygen do I need? If, figure out how much oxygen do I need if I start off with 100. Well, it's the same setup. Okay. I got 100 P2O5. Okay. And then I need 5 O2s. That's my ratio, correct? And then it is 2 P2O5 is my ratio between the P2O5 and oxygen. Okay, so how much oxygen would I need to make 100?
250.
Got it. So I would need 250 molecules of O2. Okay. Again, unit-wise, my P2O5 cancels, leaving me with units of oxygen. And so right now I'm just saying molecules, but we're going to change this to the word moles, M-O-L-E. And once we know the moles, and that's a number, big number, 6.02 times 10 to the 23rd. But once we know the number of moles, we're going to convert that to grams, because you can't go in the lab and measure moles. You actually have to weigh things out. But the atomic weight, remember the atomic weight on the periodic table? For those guys have units. Those units for all the atomic weights for all the atoms are, guess what? Grams per mole. Another ratio. Okay, so we can use that ratio of grams per mole to get this moles into grams, which is something we can actually weigh out. Okay, so this is the beginning of oh, hold on, excuse me. The beginnings of getting set up to do calculations. Now this one here, a little bit of challenge, but I'm going to let you do it at home. It says here, write the balances aqueous reaction. You're using nickel 3 sulfate, reacting it with lead 2 nitrate, and you're going to produce nickel 3 nitrate and solid lead 2 sulfate. Okay? You should come up with something like that. Now, when it comes to balancing these type of reactions, and this is a specific type of reaction, simply because we got a solid here and it's related to the solubility table. We're gonna get to this, but see if you can come up with this. And when you start balancing these type of reactions, follow the polyatomic ions, follow the sulfates, follow the nitrates. Remember, those in parentheses are the polyatomic ions. Don't take them apart, X number of nitrogens, just count them as a unit. And if you follow those along, you would automatically, just by default, balance this chemical reaction. And you should come up with 1 nickel, 3 sulfate, 3 lead, 2 nitrates, and 2 nickel nitrates, and 3 lead sulfates. Okay, we'll come back to this. All right. So, of all the chemical reactions that occur out there in nature, there's only 6 types. Okay, so a couple we already talked about. The acid-base reaction, that was one type of reaction when we talk about acids and bases. That was a neutralization reaction. But we'll get to that also in a second. The first type is a combination reaction. Now, what's written here is a general formula where you get 2 elements, A and B, come together to form some molecule, some compound, AB. A classic example here would be the reaction of hydrogen and oxygen. You ignite it, it goes boom, and you create water. Okay, so that's a good example. Hydrogen and oxygen to create water. But normally, like I said, you generally have 2 elements that come together. You're going to have at least 2 different elements to create a whole new compound. Now, the other one is the opposite, basically the opposite of a combination reaction. You take a compound that consists of A, B, C in this general example, and you break it down to its elements. You can use water as an example here too. H2O, if I hit it with some electrical current, I can break it up to send it back to hydrogen and oxygen. That's why it's so important to find water out in outer space, because we can take it, break it back to hydrogen, which is a good fuel, and obviously oxygen is something that we need to breathe. Okay, so a decomposition reaction, taking a compound and breaking it back down to the elements. Now, a combustion reaction, okay? With respect to combustion reactions, there are different types, but we're going to deal mostly with combustion of what we call hydrocarbons. And they're called hydrocarbons because they consist of nothing but carbon and hydrogen. If you got a lighter and you're flicking your wick, you're doing butane, made up of nothing but carbon and hydrogen. If this weekend you're planning on doing some barbecue outside, you're going to use some gas. What do you use? Propane, right? Propane is a hydrocarbon. The X and the Y represent numbers. The smallest number X is 1. The smallest number Y is 4. That would represent methane, okay? But they get very big. The vehicle that you burn your gasoline made up of hydrocarbons. That X gets real big number-wise. But the pre-component for a combustion, the main component for a combustion reaction is oxygen. Oxygen is a crucial reactant. Without oxygen, you have no combustion. Now, with respect to Chem 130, okay, you're only going to make 2 products when you do a combustion reaction. Those 2 products are carbon dioxide and water, H2O. Someone asked me, why is it in the gas phase? Well, think about it. You're burning fuel, it's pretty hot. So the water you're creating is vapor, okay? Next time you're driving a vehicle, if you happen to be parked in front of a vehicle waiting on the light, look at the tailpipe. Occasionally, especially the older vehicles, you have liquid coming out of the tailpipe. That liquid is water coming out. All right. Now, our engines are not 100% efficient. They're terrible. Efficiency is terrible. So not everything gets burnt. Every hydrocarbon gets burnt to make carbon dioxide. You also create carbon monoxide. And I'm aware of that, but for 10130 classes, we're going to assume 100% efficient as far as burning hydrocarbons to just generate carbon dioxide and water. Right. The other type is called an acid-base reaction. We dealt with this one with respect to the chapter on acids and bases. Okay. One, you're going to have a proton source, normally written with H up front, and A could be any multiple things. It could be chloride, a halide, it could be an acetate. Then you're going to react that with a metal hydroxide. Here's a polyatomic ion. Okay. So we have an acid, you have a water, you have a hydroxide. You always get water. You're neutralizing the acid and the base, and you create water. And then you make the corresponding salt, whatever the metal was from the sodium hydroxide and whatever was non-metal from the acid. So you get the Ma, which is normally some kind of salt. Okay. Let me clear up a little bit here. Next one. Okay, looks a little bit complicated, but let's not. Let's break it down. You can see it's pretty straightforward. But we're going to use the periodic table. Remember way back when I said I referred to the periodic table quite a bit. Why? Because there's a lot of information there on the periodic table. Okay, what we do is we take a metal in elemental form, okay, and we react it with another metal, but in salt form. So that's why A represents another metal. This could be sodium chloride, potassium chloride, but it's in salt form. And what happens if a reaction proceeds, that metal in elemental form displaces the other metal that it was in salt form. Now, the metal that did the displacing now is in salt form because it's a lot more stable in that form. And you create the other metal that was in salt form back to elemental form. You may have, you have an old car or maybe a new car that has plating, like chrome plating. This is the classic example of plating. Or you may have gold-plated earrings or gold-plated something, silver-plated, gold-plated. Okay, this is the basis of plating. You're taking a metal that's in salt form and you're plating it, converting it back to elemental form. Okay, now how do we know whether a reaction proceeds or not? Well, I direct you to the infamous periodic table. Okay, now right above the solubility rules, there's this little table there. We call that the activity series. That's a list of active metals. Now, you'll see that lithium's the first one written. Now, the ones that are underlined, those guys are very reactive. That's why they're underlined, they're bold. In other words, I stick them in water and they react like that, okay? The other metals, starting from magnesium forward, they take a little bit of extra help. They may take a little bit of acid solution to get them to react, but they will not react in water all by themselves, okay, which is a good thing because if you look at copper, you don't want copper to be reacting with water, okay? Otherwise, you can't use them for piping. Look at the last metal there, Au, gold. Gold is the least reactive metal. The way it reads that greater than means, for example, lithium is more reactive than potassium, which is more reactive than barium, etc., all the way down the road until you get to the least reactive metal, which is gold. Gold will last thousands of years underground, and it come out as pristine as it looked like when it was first put into underground, simply because it's so unreactive. Gold is normally called the noble metal, like noble gases, because it's so unreactive. Okay, we use this is a relative table, a relative listing, and it's relative to H in parentheses, which represents hydrogen gas and or water. Okay, because our reference point in this case is hydrogen gas and water. The the salt form for hydrogen is water, and the elemental form for hydrogen is H2. Okay, and that, you'll see how that comes into play here once we start doing some examples. And so in that example, that metal that was an elemental form was a lot more reactive than the other metal. Therefore, it went into the salt form. So we're going to rely on the activity series to tell us whether that reaction will proceed, okay, written here in general formula format. Okay, we'll get into specifics. Now, the last reaction is called a double replacement reaction. Now, if we look at let me see here. We see we have this pair here where we got M1, which is some metal. It's both of these are ionic. First point is this: both of the reactants, M1X and M1Y, are soluble in an aqueous solution. So they're clear. Most of them are clear, may have a little bit of color, but they're soluble. Okay. Now, you mix the two, and what happens is the anions, they switch partners. So M1, who was first with X, now is with Y. And M2, that was with Y, now I'm going to keep the colors for the metals the same. It's exchange. Okay. Now the question is, well, how do we know if a reaction proceeds? I'm glad you asked that. Okay. Because we refer to, guess what? Periodic table, and we look at the solubility rules. Now, we don't care about the reactants. I just told you the reactants are soluble. Okay. When we put them together and they exchange partners, we then look at the solubility of the new partners that have been created. And if any of the partners, any of the new products are insoluble because they're in the insoluble column of the solubility rules, then we got a reaction. If both of the products, the new products, are both soluble, no reaction. Okay? So to answer a double replacement reaction, whether a reaction proceeds, we rely on the solubility rules. And the single replacement reaction, we rely on the activity series, okay, to determine whether a reaction proceeded or not. And so this last example I gave you back here, notice here, lead sulfate, solid, okay? It is insoluble, so therefore a reaction proceeded. This is an example of a double replacement reaction. Okay, where are we at? We got a couple more minutes and single replacement. So those are the six reaction types that we have. Okay, combination reaction. Here we have two elements, phosphorus and oxygen, to give us phosphorus tetroxide. Okay, and of course we balance it out. So here's a specific example of a combination reaction. A decomposition reaction. Can anybody name that compound? Fe2O3.
Would it be iron trioxide?
Oh,
Hmm.
well, you got the iron right, and you got the oxide right, but no tri. Remember, this is they're ionic compounds.
That's right.
No prefixes. So you got iron and oxide correct. So the pairing.
So would it be
Go ahead.
iron 3 oxide?
There you go. That'll be correct. Iron 3, because the oxidation number on this iron would be +3. So this would be iron Roman numeral 3 oxide. And so in the presence of heat, actually, AKA rust. My old truck had a lot of that. Okay. Good old fashioned rust. Anyway, under some heat, pretty high heat, you can have it decompose and create iron and oxygen. In fact, industrially, this is one of the ways to take iron oxide and create iron. Okay. Of course, we're going to balance it out. Okay. Here's the balanced complete equation. One of the products here is oxygen. So anyway, this is an example of a combustion reaction. Okay. So we need a hydrocarbon, and we have C3H8. That is the general formula for propane. So this weekend, if you're cooking out, that's what you're burning, C3H8. Down here in the bottom left is the structure of it. The black represents the carbon atoms that are bonded to each other, and then the white spheres represent the hydrogen. Notice the tetrahedral configuration for all three carbons. Okay. And if these were, this was, if we had like 12 carbons all the way across, and then we have another functional group, we call that stearic acid. It's something that you find in meat. So we eat a lot of hydrocarbon, basically. They're called fatty acids. One side's an acid like acetic acid, and they got a long chain of hydrocarbon chain. All right. So the combustion reaction is we need oxygen, obviously, and the only two products we create are carbon dioxide and water. Now this has a technique to balance. To balance combustion reactions, you do this stepwise. Step number one, you first balance the carbons. Number one, balance the carbons first. Okay. After you do that, balance the hydrogens. And once you have those balanced, balance the oxygens. So those are your steps first, okay? To balance combustion reactions. So if you look at this reaction, you got 3 carbons on the left-hand side. So I can do a, I can add maybe, if I can get my, oh, if I put change the color here. If I put a 3, it's a terrible 3. 3 carbons there, okay, that balances my carbons. Okay, now I look at my hydrogens. I got 8 hydrogens in propane. I need 8 hydrogens that are in the form of water. I can put 4 right there. Okay, this was 3. Okay, so I balance the carbons first, then I balance the hydrogens. So I got 8 on the left side, and I got 4 in the form of water. Now I balance the oxygens. Total, I got 6 coming from carbon dioxide and 4 coming from water. So I got a total of 10 oxygens. Now to balance the oxygens, then I end up balancing the O2, and I put a 5 there. Okay? Does everybody look, is Mother Nature happy here? Is the question. Got 3 carbons here, 3 carbons here. I got 8 hydrogens here. I got 8 in the form of water. I got 10 oxygens, 6 of them in the form of carbon dioxide, four of them in the form of oxygen. And now I got 5 molecules of oxygen. So a total of 10. And so, yes, I have a balanced chemical equation. Okay? So for hydrocarbons, you balance carbons first, hydrogens first, followed by oxygens. Okay. I am going to stop it right here. And